You know, we tend to think of software as this pure, timeless thing, just logic, right? But what if I told you that the code running basically everything is in a constant, frantic race just to keep up with the very machines it's on?
And that's a fantastic question, isn't it? It really gets to this weird paradox in computing. I mean, if the math is solid, if the algorithm is correct, why on earth are programmers constantly rewriting it? Why does perfectly good, working code just become obsolete, even when the problem it's solving hasn't changed one bit? So, to get to the bottom of this, we're going to follow the secret life of one of the absolute giants of computational science, an algorithm called Gaussian elimination. Its journey, well, you'll see. It's pretty much the story of modern computing itself. Okay, so what is Gaussian elimination? Well, it's a real workhorse. I mean, this thing is a method for solving systems of linear equations. And that might sound a bit academic, but these equations are at the heart of, well, almost everything. We're talking computational fluid dynamics, designing electrical circuits, even modeling financial markets. At its core, the problem looks pretty simple. AX equals B. You've got A, which is a matrix of numbers you already know. B is a list of outcomes. And the whole point is to find X. That's it. The math behind this, it's been around for centuries. But the code to actually do it, oh, that's a whole different story.
So our story really kicks off with this classic conflict, this battle between two big ideas. Do you write code that's elegant and easy to understand? Or do you write code that is just brutally, unapologetically fast? So check this out. This is the first version of our algorithm, written in MATLAB. Look how clean that is. It practically reads just like the math formula. It's beautiful, right? Super easy to teach, super easy to understand. You'd think, okay, we're done. This is the perfect solution. But there was a huge hidden problem. See, the code was written to think about the data row by row, but the computers back then, which used a language called Fortran, actually stored that same data in columns. So you had this total mismatch, and it was a performance nightmare. The computer was constantly jumping all over its memory to grab tiny bits of data. Imagine trying to read a book by picking out one letter at a time from 100 different pages. That's what it was like. So what did the programmers do? They made what seems like a tiny change. They just swapped the order of two loops in the code. And suddenly, the code got, well, uglier. It wasn't as intuitive anymore. But guess what? It ran 30% faster. Just like that. And there it is, the very first time elegance was sacrificed at the altar of pure speed. But of course, the hardware didn't stand still. It kept getting faster, more complex. We started seeing vector machines, these supercomputers built for gigantic calculations, and CPUs started getting these things called memory caches, which are basically like little super fast scratch pads for data. And with this new hardware, just swapping a couple of loops wasn't going to cut it anymore. The bottleneck, the thing slowing everything down, wasn't the math. It was the time it took to just move data around.
And the solution they came up with was, frankly, brilliant. It's called BLAS, which stands for Basic Linear Algebra Subprograms. The best way to think about them is like super optimized Lego blocks. Instead of every programmer having to write their own nitty-gritty low-level code, they could just call on these standardized blocks. And the best part? These Legos were hand-tuned by experts to be incredibly fast on each specific computer.
And these Lego blocks, they evolved over time. First, you had level 1 BLAS. These were for simple things, vector-on-vector stuff. Then came level 2, which handled matrix-on-vector operations, a big step up for minimizing how much data you had to move. And finally, the big one, level 3. This was all about matrix-on-matrix operations, which is just perfect for modern CPUs. The whole idea with level 3 was to keep that super fast cache memory jam-packed with useful data, so the computer spends more time calculating and less time waiting. What this did was create what people called a transportable way to get high performance. You see, the main algorithm code, the high-level logic, could stay exactly the same no matter what computer you were on. All the nitty-gritty speed stuff was handled by those machine-specific BLAS libraries. It was kind of the best of both worlds, really. But you know what's coming, right? The hardware changed again, and this time things got exponentially more complex. We entered the era of parallel computing. We're talking distributed supercomputers, multi-core processors in every laptop. Suddenly, the problem wasn't just making one processor work fast. It was, how do you get hundreds or even thousands of them to work together without tripping over each other? And so, our poor algorithm had to change again. To deal with those big distributed machines, we got something called Scalopack. For the multi-core chips inside a single computer, programmers had to write brand new, super complex multi-threaded code in C.
That simple, beautiful formula from the beginning, it was now buried deep, deep under layers and layers of new logic, all just to manage all this parallelism. Suddenly, programmers were juggling all these new tasks. They had to manually manage how processors talk to each other. They had to synchronize everything perfectly to prevent what are called race conditions. That's a nightmare where different parts of the code basically step on each other's toes and corrupt the data. They even had to write clever look-ahead logic to guess what was coming next just to keep all those cores from sitting idle. The result? Yeah, the code was incredibly powerful, but it was a million miles away from that clean little MATLAB script. You could barely recognize it. But with everyone so obsessed with speed, a new, kind of scary question started to pop up. Okay, we've made this thing faster and way more complicated, but what if the answer it's spitting out is just plain wrong? Because it turns out some problems are just naturally super sensitive to even the tiniest errors. So there's a way to measure this sensitivity. It's called the condition number. And this is key. It has nothing to do with the algorithm. It's a property of the problem itself, the matrix you start with. If that matrix has a high condition number, we say it's ill-conditioned. A good analogy is like trying to balance on a razor's edge. The tiniest little wobble, the smallest error, and you get a wildly different result. And this is where it gets really practical. The condition number isn't just some abstract idea. It literally tells you how many digits of precision you're going to lose when you run the calculation. It's a direct measure of how much faith you can actually put in your answer. Okay, let me give you a concrete example. Let's say your computer is super precise. It works with 16 digits. But you're trying to solve a problem with a really ill-conditioned matrix, one with a condition number of, say, 10 to the 10th power. Well, that means you're going to lose 10 digits of precision, poof, right off the bat. So even though your computer started with 16 digits, your final answer is only really trustworthy to about 6 digits. All that other precision just vanished into thin air. So after this whole 30-year journey, what's the takeaway? Well, it reveals a really fundamental truth about the world of computing. It's not about software or hardware. It's about their relationship, this never-ending dance they're locked in. Think about it. Our little algorithm started as this elegant, simple formula, and it became this complex, multi-headed beast, constantly being twisted and reshaped by whatever new hardware came along. But you know what? That's not a story about failure. It's a success story. It's the story of what's necessary for software to squeeze every single last drop of performance out of the silicon. And here's the kicker. The tempo of this dance is only speeding up. Processors are getting more and more cores. The architectures are becoming more exotic, I guess is the word. The challenges are just accelerating. What this means is that programmers in the future are going to have to tackle problems that are way, way more complex than anything we've dealt with in the past. And that kind of leaves us with one final big question. We know the hardware is never going to stop getting crazier and more powerful. So the real question is, as the music gets faster and the dance steps get more and more complicated, can our software always learn the new moves? Can it always keep up with the dance?